The modern view of mathematics tends to see the best way to study a group of objects, in our case vector spaces, by studying the maps between them that preserve the essential structure. And so for us studying vector spaces, the natural thing to look at is linear maps. And it turns out that there's one type of linear map that is especially useful for helping us to understand vector spaces. And it's called the dual space. So the dual space of a vector space V over a field F is denoted V prime, and it's the set of linear maps from V into the base field. And then we say that an element of the dual, we'll denote them by Greek letters phi and psi, is called a linear functional. I don't know who came up with this dumb idea of just tacking the letters AL onto the end of function and calling it a thing, but a functional is going to always be a function to the scalar field, and that's true in any branch of mathematics. So if you've ever seen the term functional analysis and you thought it was analysis related to functions, sadly no, it's the analysis of functionals, which is a terrible thing. Okay, so let's look at an example. So if we have just good old Fn, every phi in Fn prime looks like, let's see, well, so it's supposed to be a map from V into the base field, so X is going to be our element of V here. And I'm going to say, what is phi of X? Well, it's going to be some linear function of the input variables. And then once you see that, you realize that this is just C dot X, the good old dot product, which we haven't talked about yet in this class, but I assume that you remember it from calculus. And we'll talk about it again, well, actually, I guess in 406. So a linear functional in Fn is actually just dot product against a fixed element of Fn. What else do we have? If we look at polynomials, and we take a polynomial p, then we already saw some examples of this. So the linear maps that have domain Pm and take you into numbers include integration over some set, evaluation at some point, like 0 or any other number, and evaluation of the derivative at some point, like maybe 3. So those are all examples of linear functionals. And for our first baby proposition about these things, we have that the dimension of V prime is equal to the dimension of V. And this is actually immediate by a previous result. So let's take a look. The dimension of V prime, so that is by definition the dimension of the space of linear maps from V to the scalar field, is by our previous result 3.61 the dimension of the product and so this is by 361, and the dimension of F is just 1 as a vector space, so that's just the dimension of V.